Hey everyone, welcome back to Dan91's Garage, and in this episode we're going to talk about the initial setup of the DET3 piggyback ECU using the tuning software. So we'll start off when you first fire up the program. Obviously this is what you'll see, so you usually start with the fuel table, and obviously this will all be blank. At the bottom here, that's your load axis, and the other axis up here, that's the revs. So it's always load versus RPM. Then we've got the different tables at the top here. The ignition table, again, that's the area where you're going to put your values in to retard the ignition timing. And the logging window, all sorts of other stuff. But first of all, the sort of main settings to start with, we'll start with the scale configuration, because then that'll put the correct values on these axes here and also on the correction factors here as well. So we go to setup, and then the scales configuration. So these are the default settings. So you've got a linear scale voltage, 0 to 5 volt. That's basically any 0 to 5 volt sensor. So that will pretty much cover most of the inputs. So we know we've got our map sensor going in on analog input 1, and that'll either be a 1 bar map sensor for the stock 4E FE, or if you've used a Glanzer one, that'll be a 2 bar map sensor from the 4E FTE engines. Then obviously we'll go through those. So first of all, we're going to say that we've got a 2 bar map sensor. So if you click on the load, that tells you, so you can load in a different scale, and then it comes with all these presets. So 3 bar map sensor, 5 volt linear scale, etc, etc. So if we look here, there's GM 115 kp, so that's in kilopascals, which is 1.15 bar, and that's going to be pretty close to the stock 4E FE map sensor. Now what you should do is have a boost gauge or a vacuum gauge attached to the engine, so that you can compare the readout to that versus what you end up with when you're connected to the car and it's actually pulling a vacuum. So you can actually see if the scale is correct, because for example the Toyota Starlet stock map sensor might only be 100 kilopascals, not 115, but you've got to work with what you got. So start with that one and check that it actually corresponds to what you're seeing on a physical gauge on the dash. But we're going to be turboed, so we're going to go with the 2 bar map sensor. So here we have the Volkswagen 200 kilopascals, so that's obviously a 2 bar map sensor. Again, that's the closest we've got. I don't know exactly what the Glanzer one is yet, but we'll start with that. And if it doesn't add up, so when, for example, on the gauge it says you're pushing sort of 7 psi, or half a bar, but when you read off of the scale here on the tables it says you're at 0.6 bar, that's not exactly calibrated to what you've got. So you can use the generic sort of get out of jail free card, as it were, is a 5 volt linear scale. So it will just go from 0 volts to 5 volts, because that's what all these sensors produce as far as map sensors go. They're 0 to 5 volts. So if you don't know, just use that one, and then you have to correspond what you're seeing on the gauge compared to the voltage. So then you'll know, for example, that 2.5 volts is 0 psi gauge. So we're going to go with 2 bar being right, so I can show you how this all works. So we go with a Volkswagen, and we'll compare that when we've got the actual map sensor attached to the car. Analog 2 on the DET3 Plus unit, that will be the DET3 with 400 kilopascals map, and that is essentially provided for this particular unit. So it's a 4 bar internal map sensor, so it's literally labelled as that. So we'll add that one there, because that's what the analog 2 is on my unit. If you've got something else, if you don't have the DET3 Plus, you'll be able to use analog input 2, and therefore you can put whatever sensor you choose to on that, perhaps throttle position sensor. If I was doing it, it'd either be coolant temp sensor or the throttle position sensor, because then you can have the throttle position as one of your corrections, or for sort of some of the parametric setups later on, which I'll get to, or a coolant temp sensor for other matters, which I'll come to in a bit. Then analog 3 was wideband, so they've handily provided. Mine's an AEM, so this is AEM AFR, so we'll have that one, I think. And the last one was a temperature sensor, because I've spliced into the intake air temp sensor. Now it does have its own scales here, so a guy called Pete apparently made a temp sensor with a 1K pull-up, so that might work, we don't know. So we've got a GM So we've got GM temp sensor here. So what I'm going to do with my intake air temp sensor is I'm going to pull that out and then measure what the air temperature is with a thermometer, and then see what the computer is showing me as a temperature reference to this scale. So if I choose this one now, we'll see this all changes. So we've got that sorted. So we've got the Volkswagen 2-bar map sensor, the DET3 with a 4-bar map sensor, AEM wideband, and a GM temperature sensor. So we're just going to click OK for that one. And now you can see that we've changed what the scales are showing here. So now across the bottom, we have it in bar. Our analog 2 is that one. Analog 3 is now showing air fuel ratio. So that's one of our corrections, which is good. And analog 4 is now showing in degrees C. So we've got 100 degrees C down to minus 50 degrees C. So we don't know if that's actually correct or not. So once you start the car up, obviously you'll see what that temperature sensor is reading, and it'll be hovering around in one of these boxes. And then you can measure the temperature in the air with the thermometer and find out if it's actually 30 degrees or not. Worst come to worst, we can change this one back to a 0 to 5 volt scale again. So we'll have 0 to 5 volts on there. So we know that after we've checked at 100 degrees C with the sensor in boiling water, that should take us to 0 or 5 volts, whichever end of the scale this is. And then when we've got it freezing cold next to an ice cube, or, just at room temperature, for example, at 20 odd degrees, we'll know that becomes, say, 2¼ volts or 1 volt or whatever it is. So then we can make a mental note of, if the intake air temp ever gets to 3 volts, we need to pull out some timing. But for the moment, we'll go with that until we know whether the calibration is correct. There are other calibrations in there, but this is the one thing you have to be aware of, is just because you've tapped into the sensor doesn't mean you actually have a scale here. So you might be looking at a temperature sensor in volts, but we'll see. So essentially that's that. So now your stuff should read right. So the next setting we're going to configure is the ignition configuration. So again, set up ignition configuration. And because we've intercepted the IGT wire, there are some specific settings detailed in the instruction manual, and it's quite easy to choose. So first of all, it says we have to choose the ignition mode. So obviously, being as this is a piggyback setup, we can only retard that signal. We obviously can't send out a signal from the DET3 piggyback quicker than it is sent in from the Toyota ECU. So all we can do is slow that signal down to retard timing when the car comes on boost. And thankfully, that's all we need to do. However, if you do want to advance the timing, you can physically adjust the distributor and set the base timing to 15 degrees before top dead center instead of the factory setting of 10 degrees before top dead center. So you have an extra 5 degrees advance to play with. Then, using the ignition table, remove those extra 5 degrees advance and you'll be back to stock timing. So when the engine's running naturally aspirated, you can release up to 5 degrees extra advance from the piggyback table. Then obviously when it comes on boost, you'll be retarding the required timing plus the extra 5 degrees. So for example, every 1 psi of boost added to a naturally aspirated engine usually requires 1 degree of timing retard, or 1.5 degrees to be safe. So 2 psi equals 2 degrees timing retard, etc. Plus an extra 5 degrees of timing retard to cover the 5 degrees of advance we put in physically. So anyway, into the ignition mode. So what we'll be doing is retarding a single signal. So retard single signal, because that's all we can do. Ignition input type, that's Hall effect or optical sensor. Then maximum RPM. So as we can see on this side of the table, this is our RPMs. Now, the Toyota Starlet 4EFE only revs to about 6200 redline. So there's no point in it going all the way to 7500, because obviously on these tables, you only have a set number of rows and columns. So you've got 16 by 16 tables, which is the same as the eManage Blue. So if we redline at, say, 6200 here, these 3 columns or these 3 rows are never going to get used. So essentially you're wasting part of the table. The same with the boost across the bottom here, but we'll get into the configurations of that later. So the maximum RPM, you want to set that for a few hundred RPM more than your red line. So 6200 is our red line, so I'm going to set this one at 6500. Number of signals per 720, that's 4, because that's how many signals you get for every 2 rotations of the crankshaft. and the maximum number of degrees you want to retard it. Well, I'm going to put 20 in there. I think the maximum you can have is 50 on this particular setup. So there you go. Those are the settings: retard single signal for ignition mode, Hall effector optical sensor, maximum RPM 6500, or a few hundred more than your red line. Maximum number of signals, number of signals per 720 is 4, and maximum retard 20 degrees. And obviously, because we're retarding a single signal, we've now got a grayed out option here for maximum advance, because we can't advance it anyway. So that's that. So we apply that and then click OK. And now we can see that the scale on this side of our table has changed. We're now redlining, or we now have a maximum RPM of 6500. So now we're going to get all the way up to this top row because 6200 is in there, because our next one down is 6093. And that's the top edge of this line, should be 6093, just like this one says 406. That's when you get to that line. So 0 is at the bottom, 406 is the top, not the middle, as far as I can remember. So anyway, that's ignition configuration. So the next setting we're going to look at is the setup tables menu. And this is used to configure what happens in the fueling and ignition tables and all the PWM tables and stuff. So setup tables. So this tells us what sensors we're going to use on this axis. So the map sensor, so the Glanzer map sensor we're going to be using, or the 2-bar map sensor we're going to be using. First option here is for modify. So that's asking us what signal we want to modify in the table before sending it out on the analog out. So we're going to modify the analog signal from position number 1, because that's our map sensor. So that's what's going to control our fueling. So we need to modify that signal. So that's fine. The load we're going to use is also going to be analog 1. The load option here is what moves us around the table on this bottom axis. So that's the signal we want to use. The correction for menu number 1, we're going to use analog 3, and that's already selected. And correction number 2 is going to be analog 4. This is correction 1, and this is correction 2. So you need to choose the analog input signal you want to appear here. So that's cool already. Ignition table. But again, we're going to use the map sensor in the engine bay. So the 2-bar map sensor, again, that's in on analog number 1. Correction number 1, we want to be the wideband O2, so we'll leave that as analog input 3. And correction number 2, again, that's going to be the intake air temp sensor, so we're going to leave that as analog 4. Then the PWM table, obviously one of those is going to be our boost solenoid. So that's power output 1. We're going to use that on PWM table. So again, we're going to use the map sensor to control that. So we obviously need to know the load in PSI or in bar. So we're going to use the map sensor for that as well. So that's analog 1 again. So again, correction factor, we're going to leave that as analog input 3, and then the next correction factor, analog input 4. Again, those are the two we're going to use. We're not using the internal map sensor for anything apart from data logging. So again, PWM table 2, we're not using that one, so we can go disable, disable, and disable. So if we apply that and then click OK, what you'll see is if we now have the scale at the bottom of the graph here changed to a 2-bar map sensor, where previously it was showing the 4-bar map sensor because it was using analog input 2 as its default setting. So now we've chosen it's changed to analog input 1. You can see that. You can always see what is being used. So analog input 1, that's our map sensor. Analog input 3, wideband O2. Analog input 4, intake air temp sensor. Go to the ignition table, should be the same setup. Analog in number 1, 3, and then 4. So that's cool. PWM table number 1. Again, same thing, 1, 3, and 4, because that's what I'm using for those. Because we disabled everything in the PWM table 2, you click on here, nothing, nothing, and nothing, and you can't put any values in, or it won't do anything if you do, because you're not going to be using it. So you can leave that as it is, doesn't really matter. So now the difference between corrections and the table. So the table is what they call a 3D map or 3D correction. So it works in 3 dimensions, different axes. And when you change it, you'll see sort of peaks and troughs. If you start putting in figures here, for example, you'll see these things start to pull up. So this gives you a 3-dimensional map, obviously X, Y, and then Z for the height axis. So the higher the values you put in here, the higher these peaks will get. So that's your 3D correction. But then you've got a 2D correction here. So this is obviously your table value. Whenever the load on this axis reaches this point, and whenever the RPM reaches this point, so we're going to be adding 17 extra units of fuel, which is obviously a voltage, and I'll come on to what a unit actually is in a bit. So that happens only when we're in that cell. For example, when we're in this cell, we won't be adding any extra voltage or fuel. But with a 2D correction, for example, on intake air temp, that happens all the time. So no matter what cell you're in, you can add value using this particular correction at the bottom here. You can add an extra 100% or take away 100%. So for example, if it's the intake air temps have got particularly hot because it's a hot summer's day, and obviously we're caning the crap out of it, and the intercooler isn't working as efficiently because of the higher air temps, what we can do to obviously help stave off detonation is to add extra fuel here. And this is a percentage, which is obviously shown here in the fueling table. So let's say we want to add an extra 10% of the value. So basically, whatever cell we're in this table, which is our main fueling adjustment table, for example, if we're in this one, we'll be sending out whatever the incoming voltage from the map sensor is, plus 17 units of extra voltage to increase fueling, plus, if we're at this particular intake air temp, we'll be adding another 10% on top of that to the voltage. So again, if we're in this cell, we have whatever voltage coming in plus 17 extra units. But if we're in this cell, we won't be adding anything additional because it's just 100% output. And the same goes for this. If we're in this cell, for example, we'll be adding no extra voltage. It'll just be a straight in and out signal. However, if we're in this cell, we'll add 10% to that because we think it's a bit hot. Or if we're in this cell, we won't be adding anything. So you can set up sort of these things as safety factors, essentially. You have to be a bit careful when it comes to AFRs and stuff, so don't go thinking you can make it basically auto-tune itself, so when it's lean, we'll add fuel, and when it's rich, we'll take away fuel. Because the problem with that is under certain conditions, you want it to be rich. Like on startup, for example, the ECU is going to want it to be rich, and then you're going to start pulling out the fuel, which isn't going to help on some cars. And also when it goes lean, the thing is when you shut the throttle and decelerate, it quite often goes very lean because it cuts off all the fueling because you're just coasting and there's no load and no possible damage from detonation. So if you then tell it whenever it's lean to start adding fuel, you'll be adding fuel possibly at the wrong time. So you have to be a bit careful when you're talking about piggybacks because it's not so clever with the whole wideband O2 tuning thing. So best to leave that one alone, I think. But again, as far as safety factors goes, knowing your intake air temps, that can be a good thing. So if we go onto the ignition table as well, so let's say we're going to pull out some timing here. Let's take out whatever that. So let's take out whatever that timing is. And then again, we can come down here to the degree C. So again, it's getting a bit hot again. Same scenario. So we decide that we want to pull out even more timing. So again, in this cell, we'll be pulling out 14 units and another 6 if we're at this temp. But if we're at this temp, we'll only be pulling out the 14. And if we're in this cell as well, we won't be pulling out any timing for whatever reason. This will take out more timing and this won't. So these corrections here, and also the ones in the fuel table, are always happening. They aren't dependent on whatever cell you're in here by RPM or load. They happen all the time. So you can see that whenever you're at this temperature, you will be adding extra fueling no matter what cell you're in. And with ignition, you'll be pulling out this amount of extra timing no matter what cell you're in as well. So these are sort of blanket corrections that happen all the time. So the next menu we're going to look at is the analog input. So analog inputs configuration. Now this is where you size how much of the sensor value is going to be used. So as we've already covered, this is a 16 by 16 table. And as we showed earlier, we've already removed 1000 RPM off of this axis because otherwise we would never use some of the cells. So you don't want to waste any of your cells, because otherwise if you're never going to travel up into them, essentially that's somewhere you could be using data, because obviously the more of these cells you're using, the finer your adjustments can be. Essentially what we need to do is figure out how much boost we're going to be running. So for example, half a bar of boost is going to be about 7.5 psi. So 0.6, let's say we're going to run a maximum of 0.8 or 0.7 bar on our particular build. So there's no point having the 1 bar and 0.9 bar columns in there, because we're never going to travel out of this cell into the next one, no matter how hard we go. So we'll only ever get up to this row. So what we can do is analog input 1, which is what we're using here. We change the value here, which is obviously the voltage, but you can see here, the maximum value here starts to change as well. So that's 0.7. So if we go a maximum of 0.8 bar, so now we're going to show minus 0.8 bar, which I know that when the engine's running in vacuum, naturally aspirated, it usually comes to 0.7 bar. So I'm going to leave an extra column here just in case we have a mad decel moment on overrun and actually pull a shed load more vacuum as the engine's trying to pull a shed load of vacuum. So we won't run off the table this way, basically. We're not going to go lower than minus 0.8 bar, and we're not going to go higher than plus 0.8 bar. So that's fine for that one. Analog 2, well, that's the internal map sensors. We don't need to worry about that. Again, it's a 4-bar map sensor. So you've got minus 1 bar or minus 0.8 bar and then plus 3 bar at the top. That's fine. Again, if we were using it for load or data logging, obviously you'd want to pull that back down. You'd want to pull that back down to the intended boost you were going to run. So if you're only going to run 2 bar of boost, you obviously want to pull this down till this says 2.1 bar, because otherwise you'll be wasting cells again. But being as we're going to use a 2-bar map sensor because that's more appropriately sized to our build, then we're not going to bother with that one at all, apart from data logging. And AFRs, we're going to leave them alone because we are going to want to see the full range that the sensor can produce. So that's fine. And intake air temp sensors, well, I doubt we're going to get to 100 and I doubt we're going to get to that. But what we'll see is you'll have to see, I mean, we're not going to get down to minus 50 in the winter, for example, because we only ever get down to minus 30 odd, I guess. Not even that. I mean, the worst thing we had was the beast from the east, and that was minus 20. So, for example, the coldest English winter, we'll say that was minus 30, for example. So we'll mess about with that until we're at minus 30. You get the idea. And 100 degrees C on intake temps, well, that's possible. So the whole point is, you need to shrink these values down to the least possible while still covering all of the potential your engine will produce. So you don't want to run out of table this way, and you certainly don't want to run out of table this way. So there we are. And if we do that, now we can see that this bottom row has changed. So now our last column is 0.8. So now we've got minus 0.8 to plus 0.8 spread over 16 rows, rather than minus 0.8 to 1 bar spread over 16 rows and not using the last 2. So that's the whole point of this one, is to size everything so it's correct for your build. The thing is, sometimes you'll actually have to run the car and drive it a bit to know. So for example, I started mine up at idle just to find out what the vacuum was going to be, so I knew that I really wouldn't be taking anything off this lower end. But there we go, the top end, that's easy. I mean, assuming this is actually 0.8 bar, because we don't know if this calibration is correct for our sensor yet, but if not, this will be a 0 to 5 volt. So for example, if this is in volts rather than in bar, what you'll have to do is find out how many volts it is for vacuum and then use that as your bottom end of the factor, and then also find out how much boost you're getting into from a few test pulls, obviously with a bit of safe fuel and safe ignition timing retarded. And then you'll find that, for example, 0.7 bar gets you to 3 volts here. and you're not going to go any higher than that, then set the maximum at 3.5 volts so you can then adjust your tables that way. It is possible to do it with voltage, because at the end of the day, all it is a voltage signal in and out. So you just need to find out what column corresponds to what particular boost pressure by comparing it to a gauge on the dash. So next we're going to look at the analog output configurations. And again, more voltages with minimum and maximum values. So the minimum voltage output from the analog out, which is our modified signal. So that's going to be the 2-bar map sensor to control the fueling. So the minimum voltage we're going to send out to the ECU, and the maximum voltage as well. So for example, if you get boost cut on a sensor at perhaps 4.8 volts, you can change this to 4.74 apparently. So then the DET3 ECU will never send out a signal higher than that, no matter what the input voltage and no matter what you put in this table to add to it, for example. It will never send out more than 4.74. So that's how you defeat boost cut essentially. So that's the other danger of it, is you remove your boost cut by doing that, because you're lying about the maximum voltage being sent. The analog out offset is a voltage, so you can add or take away a blanket sort of change. So for example, if you're sending out 3.5 volts, but that's not enough, you can then add to that in here or take away. We don't need to use any of that. I seriously doubt I'm even going to bother putting in a analog output max to defeat the boost cut, because at the end of the day, if we ever get to 4.8 volts on a 2-bar map sensor, we're going to be higher than the 10 psi or 0.8 bar that I've requested anyway. So I don't really want that. So I'll probably leave that a maximum of 5 volts. That way you keep the boost cut. For startup voltage, well, the startup voltage, essentially some engine management systems want to see a certain voltage from the map sensor at startup, say for example 2 volts, and because it takes a fraction of a second for the DET3 to initialize, it may send out a signal of 0 volts, and then the engine management will throw a code. That doesn't happen on the Starlet, so we don't even have to worry about that. And the last one to look at is the analog signal modification step. Now, this relates to the analog stuff, which is obviously fueling, and in this table you can put a maximum of plus or minus 127 or 128 increments or steps or figures, whatever you want to call it. And each one of those figures relates to whatever value's in here. So depending on how much voltage you want to add or take away, you need to choose what each of those steps is worth in a voltage. So for example, if you need to add a shed load of fuel, you might want to bump this up to a higher value. So I'm going to start in the middle basically. So there's 3 different settings here: 0.0049, 0098 and 0195. And if you obviously times those as a volt by the 127 or 128 steps you can use, you'll obviously end up with, on its finest adjustment, a maximum plus or minus of 0.625 volts. On the middle setting, it'll be plus or minus 1.25 volts. And on its coarsest setting, it will be plus or minus 2.5 volts. So that means, for example, if you're sitting in the middle here at 2.5 volts and you put in the full value, you will be able to send that 2.5 volt signal up to 5 volts or down to 0 volts. So that's pretty coarse, but you've also got to realize that every step you put in obviously adds more fuel or takes away fuel. And if the adjustment's too coarse, you might not be able to add a small enough amount to get the desired air fuel ratio. So that's essentially what that's for. Again, the smaller the value, the finer the adjustments, but you might find that they're too fine and you run out of steps because you're limited by 120, because it's not done in milliseconds of injector pulse, for example. You're just adding voltage or taking away voltage. So you need to be able to add or take away enough voltage. So I'm going to start in the middle and go from there. So that's basically it. So we'll look at the saving of this now. And the first thing to do is the scales configuration, because whenever you fire up the DET3 software, it fires up with a default set of scales here. Now, I can only assume that's because you might be a tuner using this software to tune many cars, either turbo or naturally aspirated or nitrous or whatever. So you're going to need to have a different set of scales for each tuning job you're doing. But being as most people are going to be using this to tune their own car, they're never really going to need to change those scales. So when you save all the other tables and maps that you've modified with all the other settings, they actually get saved, but it doesn't save your scales configuration. So every time you fire this up, it will be on whatever set of scales it is here. So these are what we want for our car. So we're going to save this as video. Hello, crazy hands. Test scales. So we've now got a set called video test scale. So that's what we're saving that as. Now, if we change the default scales, load in video test scales, for example. Now, every time we fire up this program, it will come in with the scales that we've set up for our car. So that's a nice tip, because otherwise every time you fire up the program, it'll be on default scales and you'll have to go back and either load them if you haven't chosen to use them as a default, or set them up again if you haven't saved them. So that's something I learned the hard way. Every time I turned the software on, I went, where have my settings gone? So that's cool. So next time we fire the program up, it will automatically pull in the right scales to display here. So that's that. The next one is obviously to save the actual data. So for example, if we go to the ignition table, and obviously we're set up for turbo, so we're just going to rough in some values here. I'm not saying this is what anyone should use on their car, we're just going to put something in so I can show you something to save. So we'll go -1 degree there at about 0.1 bar of boost. And then we're up to 0.8 here. So I don't know, let's take out say 12 degrees of time in there. So we've taken out 1 degree of time in here, 12 degrees of time in here. And obviously with the wonder of interpolation, we select between our -1 and our -12. Choose interpolate, and what that does is it fills in all the blank cells in between evenly with the values between the minimum and the maximum you selected. So that's now filled those in rather than having to work out what each bar should be. That's roughed in our timing values for us there. So that's retarding timing on boost. What we've also done obviously though is we've set our timing to 15 degrees before top dead center rather than the specified 10 that Toyota usually want us to have. So what we'll do is we'll select the entire map there, as you can see, and then we'll take out another 5 degrees of timing. So now everything has got an extra 5 degrees taken out. So now we're back to naturally aspirated section here. We're back to -5 degrees off of our 15, so that gives us 10 degrees before top dead center or stock timing. And when we come onto boost on this side of the map, that will essentially have -1 to -12 here. So anyway, those are the figures I'm roughing in just so we've got something to save. You're not going to need any additional timing there. So again here, so the whole point was we can now advance the timing a little bit. So for 2000 RPM to redline, naturally aspirated, we're going to want, say, an extra 2 or 3 degrees. So what we'll do is we will add an extra 3 degrees. So now we're only taking out -2, which means for this section of naturally aspirated map, we're now running with an extra 3 degrees of timing above stock. So that should give us a little bit more zing there. So that's it. So now we have a table. Again, we'll do something here. So yeah, this one, we'll take out another, when we're getting hot, we'll pull out another 2 degrees there just to make it safe. So there we go. So we now have a pretend map, and now we'll save it. So you click on save here, and this gives you examples. NA test project and turbo project. I've already been playing about this obviously, so we'll call this video test map. Just for the fun of it, we'll save him in there. So now we have a map saved onto the hard drive of the laptop itself. Now obviously, when this is connected to the DET3, the DET3 is basically using, from what I can work out, the best way I can describe it is it's using the laptop as its memory tables to refer to. Obviously, when you disconnect the laptop, you need to have sent those tables and the data and everything and the configuration into the DET3. Otherwise, the DET3 isn't going to know what to do, because all of the changes so far, we've done them in the table, we've now saved them to our hard drive, but now we need to send them to the DET3 itself. So it will actually do something when we've disconnected the laptop. So the next button next to this, if it was connected to it, wouldn't be grayed out, and you click on that, and then that makes the maps permanent. You have to have the engine off, but the ignition on to send them to the DET3. And obviously you should only do that when it's safe to do so. So yeah, that's basically it. If you've got any comments or questions, please write them down in the comment section. That's what it's for. I will always try and get back to you. Hope you enjoyed it. Hope you learned something. If you did, it only takes a second, but please press the like button and subscribe for more of this content. The more likes I get, the more subscriptions I get, the more it spurs me on to make videos like this. I hope you guys enjoyed it. My name's Dan. This is Dan91's Garage, and I'll see you on the next episode.